Hi, this is Pratik and welcome to Code Verify. In this video lesson, we'll learn about the problem that is associated with multiple recursion calls while doing depth first traversal. So as you have seen in my previous tutorial that I did depth first traversal by using recursion calls. So these recursion calls are actually function calls. So these function calls are basically handled by the Python call stack. So whenever a function call is made, a stack frame is appended into the Python call stack. So whenever there are multiple recursion calls, the call stack keeps on getting filled. That is, stack frames are continuously being appended into the call stack, and the call stack's frames are popped from this call stack whenever the function returns. So the problem with depth first traversal is that since it uses recursion, and if the depth of the graph is very large, that is, it is very deep, then the call stack will be keep on getting filled and it may reach up to its limit. There is a very interesting way in which we can determine the recursion limit in Python. For this, we got to import the sys module in Python, and after this we're gonna use the sys module to print out the recursion limit. So if I run the same program, you see that this was the output from my previous tutorial, and this is actually the recursion limit, that is 1000, or I can say there can be at most the length of the Python call stack is 1000. That is, it can hold up till 1000 stack frames. As I've told, that stack frame basically contains the name of the function that is called and where to pick up from when the function call returns. So the call stack length is 1000. Now I'm interested in finding out the call stack, the length of the call stack that is being utilized in this code. So I'm going to do a bit of modification to print the amount of resource in the call stack that our code uses. So I'm gonna use another module called inspect, and this will help us inspect the length of the call stack that we are using. So let's print out the initial stack length before we actually call this DFS function in the main. So I'm going to print the initial stack length when we are starting from the DFS function. So if I run this program, then you're gonna see that the initial stack length is 5. So stack length is 5, which means there are already 5 stack frames in this call stack, and these 5 stack frames could have basically been possibly coming from these function calls. These are actually function calls that we actually made before we actually call this DFS function here. So basically that length 5 denotes that before we actually call this DFS function, the stack already had something and the length was already filled up till 5. And also I had when I made an object of the class graph, it called the constructor, which is actually type of function. So maybe the stack built a stack frame out of this, and therefore the length of the stack was initially 5. So the initial stack length is 5. So now when we move forward and we call this DFS health function, then the stack length will be increasing by 1. And so when we call the DFS health function, we move here. So in this, when we move to the DFS health function, I am gonna print the stack length again. That is, when we are in DFS health function, it's gonna print the length of the stack, that is the length of the call stack that is used. And also I am gonna add a break line here so that the output looks a bit smooth. So if we run this program, we're gonna see that it started from stack length 5, and then it called the DFS help function so here it called the DFS help function, which means the stack length should have increased by 1. So as you can see that when we entered the DFS help function, the stack length got increased to 6, and then 0 was printed. So this 0 is actually the vertex 0, and it has got nothing to do with stack length. So this is the stack length, and now the stack length 6, and then we move forward, and after printing 0, we entered into this for loop, and then we again called the DFS help function recursively, which means the stack length should be getting increased by 1 again. So as you can see, the stack length got increased by 1, and it became 7, and then it printed 1. And then again it entered the for loop, and again it called itself recursively, then stack length increased by 1 again, and 3 was printed. Again, you can see that if you're not getting confused, then the graph that we used was this. That is, we start from 0, then 1, then 3, 4. So like we moved from 0 to 1, then the stack length increased. Again, we moved from 1 to 3, the stack length increased. So now the stack length is 8, and it printed 3. Now we again entered the for loop, and this time from 3 there was no other way. All right, the only way was back to 0, but 0 was already traversed, so the function was not called again. Okay, because the function is called recursively when we are traversing a node for the first time. So when from 3 we go back to 0, this if statement fails, which means the function call doesn't take place, which means when we are at 3 and the stack length is 8, and we cannot go anywhere further from 3, therefore we move back to 1. So when we move back to 1, which means the stack frame for 3 gets popped out, and the stack length becomes 7. But when the stack length becomes 7 and it comes back to 1, then from 1 there is again a way to 4. So from 1, when we go to 4, then stack length increases by 1 again, and it gets increased from 7 to 8. So remember, when we go back from 3 to 1, it becomes 7, and when we go from 1 to 4, it again becomes 8. So therefore that's why we see that it remained 8 here and printed 4. After this, there is no way out from 4. So from 4 you can go anywhere. So here the stack length was 8. We cannot go from anywhere from here, so you go back, okay, and you reach here. Again, from 1 you have already traversed 3 and 4, you cannot go anywhere else. You could have gone to 0, but 0 is already traversed, so there won't be any function call, so you cannot go to 0 again. So from 4 to 1, when you reach 1, the length again becomes 7. That is it gets decreased by 1, and from 1 you again go back to 0. When you again go back to 0, the length becomes 6. All right, and from 0 there is a way out to 2. So from 0 you go to 2, and the stack length becomes 6 plus 1, that is 7. So therefore when you reach 2, the stack length becomes 7, and again there is no way out from 2. So therefore you again basically go back to 0, and the stack length decreases by 1. That is the stack frame gets popped out from the called stack, and it gets decreased by 1, and now it becomes 6. So now the stack length is 6, and basically you are done with 0 also, because you have traversed this way and this way, so there is no other way you can possibly go. So now the stack length is 6, and it exits 0. So when it exits 0, which means the stack frame associated with 0 in the call stack gets popped out, which means the stack length again gets decreased by 1, and it becomes 5. So the only thing left to be traversed is 5. So since this is a discontented graph, so you cannot go to 5 years by 0. So you're already done with 0. The stack length is 5. So now you basically traverse to 5. So when you traverse to 5, It means there is again a function call and the stack frame is appended into the call stack. So now the stack call stack length becomes 6. Therefore, in the output you can see that before printing 5 the call stack length becomes 6 and then it printed 5. So now after everything gets over, we are done with overall DFS traversal. I am interested in printing the length of the stack used, and that I do by this. And I'm also interested in peeping into the call stack to see what it really contains. So I can peep into the call stack by using inspect.stack. So if I run this program, then you see that the final the stack length that was used was 4. That is when we are executing in this line. So this line, when this line gets executed, it prints 4, and this is actually what is inside the call stack when we are finally done with everything. All right, so here it's basically a bit difficult to explain the content of this call stack. As I had said, that this call stack basically contains stack frames, and these stack frames contains the name of the function call and where to go when the function returns. So as you can see that this frame info basically gives information about the stack frame, and there are a lot of complex things out here which I won't be explaining right now. So if you understand, or you can just Google it out how to read a stack frame, I think it would be of great help. But for this tutorial, it was important to understand the Python called stack frame and how actually the recursion call take place. So you see that the maximum limit of recursion call is 1000. All right, so there can at most 1000 stack frames into the call stack. So if the length of the graph is too big, it is too deep, then there will be more function calls, and all this function call will result into a stack frame being inserted in the call stack, and this is going to fill the call stack, and up to a certain limit, that is 1000, you cannot do more function calls. And when that happens, our code is gonna fail. It's gonna return a runtime exception error saying that the call stack limit has exceeded. Therefore, to overcome this problem, we're gonna use the concept of stack of iterators. So basically, this DFS traversal can be done by using a stack of iterators. So I'm going to speak about stack of iterators now. So in stack of iterators, you do not use a recursion call. You simply use a stack. You maintain a stack, and the stack is basically a Python list. Okay, so you maintain a Python list to go as deep as possible to do depth first traversal. And the benefit of using this list is that the size of the list can be exceeded as much as per your requirements. So if the length of the graph is too deep, then the list will be huge, but that's not a problem, because it's a problem only with recursion, because the limited size of the call stack. But the list that we'll be using in stack of iterators, it can be expanded as per your limits. And also popping and pushing into a list is easier than a function call. So our stack of iterator style of coding will be actually way more faster than this overall recursion calls that we dealt in the last video tutorial. So I'm gonna basically continue from here and show you how to use the stack of iterators to do depth first traversal, and that I'm going to do in the next video. So stay tuned, and thanks for watching.